Okay, then let's continue. Next presentation will be given by Tobias Fellmeth, who is a senior researcher at Fraunhofer ISE, and he's from the HighLite project. And Tobias will talk to us about minimizing cut-edge losses in advanced silicon solar cells. Tobias, the floor is yours.
Can you hear me, everyone?
Yes.
All right. Thank you very much, Michael, for the nice introduction. Welcome, ladies and gentlemen, to my talk about minimizing cut-edge losses in advanced silicon solar cells. When you look on the ITRPV roadmap just recently published, you see basically a trend towards larger wafer sizes within this decade. And this implicates also increasing need for half, tree cut, and shingle module concepts. And when you look on TaiyangNews report, which are very good to read, you see already today that lots of companies using half cells or three cut or shingle cell module. And for example, here you see also an image from a Trina Solar Vertex module from a G12 wafer, which is an edge length of 220 millimeters, and also the sun power, which is into shingling. So therefore, edge recombination obviously plays a tremendous role in these new concepts, and also we have a general trend towards higher efficiency. Therefore, we need to look on edge recombination. So here you see a generic cross-section of a solar cell where you have an emitter and a bulk and a back surface field, and usually the wafer edges are passivated. This is due to the fact that in the end of the front end, you have the PCVD processes, which are normally wrapping around also the dielectrics around the edges, and therefore you get a let's say already a decent passivation. However, when we then start to cut those cells, normally a laser is used, and the laser penetrates your wafer, melts the silicon, and leaves a morphed silicon behind. And then you don't shoot through the wafer, you basically mechanically cleave then later on. And when we look on such edges, we can distinguish in two domains. Basically, the space charge region, the open. We have an open p-n junction, where when you consider a p-type bulk and an phosphorus emitter, where the electrons generated in the bulk can easily travel via the emitter towards the edges, leaving here. Looking in a K-space diagram, the conductive bands are leaving here lots of electrons in the conductive bands, and then due to the dangling bonds you have on the surface here, which is characterized by the trap density at the interface, these electrons can easily recombine there. And this recombination mechanism over the space charge region is known in the literature by a chain or two-like recombination. At least it is a recombination where you have ideality factors of greater than 1. By approximating this, you can calculating a chain or two-like behavior. And you're looking on the second domain, where we have the bulk basically. We have less free electrons, as you can see here. However, you have compared the thickness of this is way bigger than the space charge region. Therefore, you have also a significant impact of this kind of recombination. And this I will show later, is also a J02-like recombination, and also a J01 where you have a little bit VOC loss there also. And here, and by using Crocker 3 simulations, you can basically look on the different recombination channels and see what happens there. And when you consider a 20.5% solar cell, a full-size solar cell with 0 edge recombination, you can then basically switch on and off all the mechanisms you want to see. So you have basically the perfectly passivated solar cell. So this would be the 20.5 here, or the 23% with the recombination velocity here on the surface recombination velocity, very complex word, of 0. And then here rather theoretically a state where you have an open unpassivated PN junction, then something like a bulk recombination only, so meaning edge recombination here only without an open emitter. And then, of course, the normal configuration where you have an open emitter here also on the edges. And by switching on, for example, the space charge region recombination only, you see basically it is, so this is the blue bars, it is basically a fill factor loss you see, and this is comes due to a pseudo fill factor loss. And you see here also VOC and short circuit current are hardly affected. And then by switching off the space charge region and switching on the bulk recombination, so having this now, the emitter window case, then you see also basically a pseudo fill factor loss. Yeah? And also a nice finding here is that when you just turn off one channel, then you still having a great impact of your edge recombination, yeah. And you need to basically shut off the open junction recombination and the bulk edge recombination to really reduce the impact of the edge recombination. And of course, by making the cells better and better, the edge recombination starts to induce the losses quite severely. And then also VOC losses are starting to be significant. Huh? And thinking of a heterojunction solar cell with very high VOC, you will see also a tremendous VOC loss besides the pseudo fill factor loss. And why we have here mainly pseudo fill factor losses, you can easily see here. When you use such big wafer and you make a PL signal detecting just here, you get basically the PL signal without any edge recombination. Then you cutting out the square, and then you measure PL again, and then you make a line scan. You see here the blue one, which is not affected by edge recombination, and the yellow one, which is affecting. So, and you see at VOC conditioning, you have towards the edges a strong bending. However, throughout the whole solar cells, you basically see no change in PL, meaning that in VOC, you have no or only very less losses. And at MPP condition, it's different. You see there a way more severe impact of the edges, leading to a reduced PL signal. And this fact leads to a pseudo fill factor loss, mainly due to the edges. So we can, as a takeaway here, edge recombination mainly leading to pseudo fill factor losses, and secondly to VOC losses. And thinking of passivating the edges, we need to think also of very smooth and passivatable edge. And what usually is done, with a laser is shot into the solar cell, and then it's mechanically cleaved. So this is in short laser scribing and mechanical cleaving, LSMC. And what we are doing is thermal laser separation, short TLS, where we have initial very small scribe with the laser. And then by combining a heating laser, so with reduced power compared to this one, and a cooling where we induce compressive and tensile stress simultaneously, we can guide a crack along a desired direction. Therefore, the cell is separated. And when you look on such edges, in the case of LSMC, you see here the areas where the laser penetrates, so where the silicon is molten, they have the amorphous structures, and here the cleaved area where it's very smooth and how it should look like. And comparing this to the TLS edge, you see basically the whole cell. So this is metallization, right? So this is the silicon here. You see the whole structure very smoothly cleaved here. And so having such a nice edge, we also need to think of how to passivate then it in the back end. So after the separation, and what we're using here is a thermal ALD process where you have TMA and basically water as precursors, and deposition temperatures below 200 degrees, way below 200 degrees, and these passivation needs to be triggered also with an using an anneal below 200. So this comes already with a compatibility also to heterojunction solar cells, taking into account these very low temperatures here. Okay, so how to characterize the edge recombination? We did a little experiment, and you see here a host wafer where we have already here some shingles printed on this host wafers, and we can just use the SUNS-VOC measurement to measure this host wafer. And then we basically do LSMC and TLS, cutting these into shingle cells, and then measure again SUNS-VOC. And then we use our thermal ALD process on both shingle solar cells, and then we do the anneal, and then measure and measure over and over again a SUNS-VOC. So we have 4 SUNS-VOC measurements in total, and this is what come out. So in the beginning, you have the host wafer SUNS-VOC, and also it comes with a reference measurement where we do just nothing and measure always. And by looking on this measurement, you see whether we have any artifacts along with the measurement itself. So then we can separate the cells and then measure it in the shingle states. So basically all wafers or then shingle cells drop. You have here the LSMC cells, the TLS cells, and aluminum oxide passivated and without passivation, and basically everything drops quite similar. However, then we start to deposit aluminum oxide, both pseudo fill factors getting a bit better with a minor increase of deposition. And then we do the annealing, and then you can see basically here that with the LSMC group, it doesn't change here at all. And also with the without group, there is no change. And you see only a change in the TLS group. So that means that you not only need to have a good passivation layer, you need also look on your surface. So by just using a standard conventional separating process and then trying to passivate it, it won't work. You need a smooth surface in order to passivate this. And looking now on the stability of these passivation, because we have seen here also without any aluminum oxide deposition, we see a little increase in the pseudo fill factor. However, this is unstable. This is a native oxide effect. And when you look on the this time experiment here, you see a cell or cells which has a very thin aluminum oxide, and here a rather thicker one. So it's still nanometer, right? And here without any, so this is TLS cut, all 3 are TLS cut. And you see here that you basically get, after annealing, the gain, but then you start to lose again. not to the initial level, but however you're losing. So you need here a certain thickness of the aluminum oxide layer to really remain stable. So this is after over a week. So having a stable cell. And here you see also the effect of the native oxide. The native oxide grows, improves the pseudofill factor, however, drops again. So it is not a stable process. You need to use at least aluminum oxide with a certain thickness. Okay, so what comes out by doing solar cells? So we're having this shingle B-perk solar cell. And we can see here, we're reaching here an efficiency of 21.7. And then using our passivating edge technology, PET, we're reaching 22.1. And since it's a bifacial solar cells, we can add also some rear illumination here, considering additional 100 watts per square meter. We're reaching then finally milliwatts per square centimeter power output of 23.5 with the shingle B-perk solar cells having a passivated edge, and compared to a 23.1%. So we're having here a gain of 0.4% in the efficiency due to PET. And so coming to the end of the second part of the presentation, we also trying to model all this. So by using the combination of COCA3 and PL imaging. So again, you notice this images here. We can spot here a region of the wafer, and we can here within the wafer looking on all the properties, so the lifetime and the J0E and everything which comes along this region, and we can feed all those parameters we can characterize into COCA3, and then we cut our square we're looking to, and then after cutting we have then the edge affected wafer, and then we can measure at different states we want to look at, and a different illumination laser intensity, measuring the PL and feeding this into the COCA simulation, and then we just fit these two parameters, the J02 edge and an S effective, to the measurements here, and then we getting a nice fit, and also getting these parameters, and this is done by minimizing.
Just 1 minute.
I'm done. Nearly. We basically minimizing the mean square weighted deviation. So we're getting then, where it's minimizing, we're getting a doublet of the J02 edge and the S effective. And we see that it very nicely fits all the PL signals we measured, and then we can combine, or we can characterize all the edges we have, and we can see that the mechanically diced edge has the most severe parameters, and then by TLS cutting the cells, the J02 and S effective is reduced, and then of course by switching off the space charge region recombination by introducing a emitter window, we can reduce the edge recombination further. And TLS plus PET is in publication at the moment. I cannot reveal it here. That wouldn't be fair, but I can tell that it's tremendously reduced compared to the others. And this brings me to the end of my talk, and in the summary, and we have seen that looking on the IT-RPV trends, we're having a trend towards larger wafers implicating half, tree, and shingle cut module concepts, and the edge recombination. We've seen that the edge recombination leads mainly to pseudo fill factor losses, and secondly to VOC losses. We need to have a way to having smooth passivatable edges, and therefore we're using the TLS. And we have seen that by conventional laser scribe, we're having an edge which is not passivatable. And the passivating edge technology, PET, is using thermal ALD, aluminum oxide for that. We have low deposition and annealing conditions, which is also compatible with heterojunction solar cells. And we see on B-perk solar cells with PET 0.4 gain over the conventional LSMC scribed cell, and combining this with a real illumination, we're ending up with 23.5. Oh, this is wrong. Milliwatts. Should be milliwatts per cubic centimeter square centimeter. And with the edge recombination properties, we can be using a Crocker 3 and PL fitting mechanisms to reveal the edge recombination parameters. All right, thank you for your attention. Any questions?
Thanks, Tobias. I think we have to, you have to answer the questions on the chat. Actually, I think there are a couple, I've seen that, but we're running a little bit behind. Thanks a lot. I think that's an important topic and great results, because everyone is moving to half cell, triple cut cells. I think at SNEC there were even some 4-cut cells shown. So I think that's the way to go, and great work. Okay, so. Thanks again.